All right, the 1.65 gram sample of aluminum reacts with excess HCl, and the liberated hydrogen is collected over water at 45 degrees C. So we have hydrogen gas. 25 degrees C or 298 Kelvin. At a barometric pressure of 744 millimeters mercury. What volume of gaseous mixture in liters is collected? Okay, unfortunately, this is not 760. If it's 760, then I could use the one I've memorized. And so this one I can't use the one I've memorized. So did you already do how many moles of hydrogen? Did you calculate that? How many moles of hydrogen did you get? 0.091. Okay, we need more sig figs. Because this is 3 sig figs here, so we should at least get 3 sig figs minimum. Sig figs I usually just take off like a tenth.
0.09173.
9173. All right, so we have two different choices. One, we could use the molar volume, or two, we could just use the ideal gas law. In this case, I would just use the ideal gas law. One, I mean, this is probably just a one-off calculation. One-off calculation. If I was doing multiple calculations, I'd probably do more. So this is nRT over P. The trick is this. This is the temperature of hydrogen. We have the temperature of hydrogen. This is the moles of hydrogen. But, is this the pressure of hydrogen? Now, we have two different hydrogens here. We have wet hydrogen and we have dry hydrogen. And so when we do a measurement of the pressure, we can't separate the water from the hydrogen, the water vapor from the hydrogen. And so this is going to be the pressure of the wet hydrogen. So this is a bit of crucial information here. So this is wet. However, this moles, this is dry, because this is the calculation just for the hydrogen itself. So this is going to be for dry hydrogen here. And so we can use this. We have the temperature of the wet hydrogen is going to be equal to the temperature of the dry hydrogen, because they're in the same container. And so we have the temperature of the hydrogen here. It's just the pressure. And so we can't use this pressure here. We can't use it because it's a mixture. And we could use it actually. If we did this as actually, I don't know. So here, what we want is we want the volume, and the volume is going to differ depending on how we visualize this. So if we visualize this as a Dalton's mixture, all the volumes are the same. So the volume of the wet hydrogen is equal to the volume of the dry hydrogen, which is equal to the volume of the water vapor. But the problem is the pressure isn't all going to be the same. So we have to figure that out. So they don't give us the information. So we have to look it up. We have to look at the vapor pressure of water at 25 degrees C. Actually, that number I don't have memorized. So let's go to the vapor pressure table. This is looked up. So what is the vapor pressure of water at 25 degrees Celsius? That's what we're going to look up right here. Yeah. So at 25.0 degrees Celsius, the vapor pressure of water is 23.756. the pressure of the wet hydrogen is equal to the pressure of dry hydrogen plus the pressure of the water vapor. We just call it pressure of H2O. So the pressure of the wet hydrogen is 744 millimeters of Hg. Pressure of dry hydrogen we don't know, but the pressure of the water vapor we just looked up in the table. It's 23.7564. But you know that a torr and a millimeter of mercury are the same. And so we can calculate the pressure of dry hydrogen there. Once we get the pressure of dry hydrogen, then we can plug it into our equation here. And so this, they didn't give us the information. We had to look it up in a table. Okay, is that okay for this one? What was the next question?
82.
82.
Is it 764 or what is it? From tor to bar, is it 1.0155 or is it exactly 12?
My math.
Yeah, 764
Yeah.
is 1.0155 bar.
Okay. Just make sure.
As long as you know that bar is
I'm trying to calculate 744 millimeters hydrogen into bar, which is 0.99191. Okay. It's fun to do random equations to help yourself memorize.
All right. For some reason, this is low. But 82. A sample of nitrogen diffuses through a tiny hole in 38 seconds. What must be the molar mass of a gas that requires 64 seconds to fuse under identical conditions? So this one we use the famous Graham's law of diffusion and the effusion for this. The equations of kinetic, did you memorize these?
Just Graham's law.
Equations for kinetic molecular theory are just going to be given. Sorry, Alex, but it's good to memorize it though, for sure. But anyway, we have the rate of gas 1 over the rate of gas 2 is equal to the square root of what?
MB over MA.
Yeah. All right, I'll call this A, be consistent here. We'll call this B. MB over MA.
2 over M1.
Yeah, that's fine. They're inversely proportional. And so it's just inversely, but the rate is also inversely proportional to what?
Temperature TB over TA.
Not the temperature.
Or it's TB over TA.
Yes, it's TB over TA, but it's not temperature. What was TB over TA? Yeah, you need to know what the T stands for. I mean, if I write it on the board and it needs clarification. Time, right. That's what the T was. It was time. So not only is it inversely proportional to the square root of the molar mass, it's also inversely proportional to time. TB over TA. Because the slower the rate, the longer the time, the faster the rate, the shorter the time. So the sample of nitrogen infuses through a tiny hole in 38 seconds. So we'll just call nitrogen, we'll solve for B. We'll call nitrogen A. And so that's going to be down here, 38 seconds. and then the square root, and the molar mass of A is 28.02 grams per mole. All right, and then the other one is in 64 seconds here. And then the molar mass of B, we don't know. That's our unknown. So what we'll do is just square both sides and multiply by 2802. Is that clear?
Yeah.
Okay. Okay. Other questions?
Number 87.
Okay, recalculate the pressure of chlorine gas by using both the ideal gas equation and the Van der Waals equation at temperatures 100, 200, and 400 degrees C. From the results, confirm the statement that a gas tends to be more ideal at higher temperatures than at lower temperatures. You know what I'd like to do for repetitive calculations? I'd like to use Microsoft Excel to do this kind of stuff. It comes in handy. Right, that's what we're going to use today. Microsoft Excel. We're going to make a little spreadsheet here. So the first thing is I'll plug in the temperature in Celsius. So normally when we do this, you could insert, you could insert the degree symbol here. Let's go ahead. If we go to insert, and we go to symbol here, go ahead. This is the problem I had in Canvas. I was trying to insert the degree symbol in the grading rubric on that, and I could insert it in the question, but I couldn't insert it in the answer, and I didn't want to waste too much time trying to figure it out, and so I just wrote it in the question, the degree symbol. But I know a lot of people ended up expressing their answer in degrees Celsius or Celsius. They marked it wrong. Does somebody know? There's also a code for this. I don't remember the code.
176.
There's a 176. Thank you. Okay, so the first temperature was 100. The second temperature was, what was it?
200.
200 and then 400, right?
Yeah.
And so it doubled each time. And so the first thing I want to do is I just want to get the Kelvin temperature. And so in Excel, if I wrote the units here, then I can't use these numbers for calculation. And so I put the units up here so that way I can use these numbers for further calculation if I want. And then I'm just going to center everything here. All right, so I need the Kelvin temperature. And so we'll just write it like this. So I'll just do T/K. And to get the units are Kelvin, this is the temperature. Usually I use uppercase T for temperature, lowercase t for time, but that's not always the case. Okay, with Excel, I can just type in the equals. So I'll type in equals here, and that sets up the formula bar here. And so I'm just going to go equals this plus, so I'll do 273.15 Kelvin. And then I don't want to copy that over, so I'm going to just click on this cell here, and then this little right-hand corner will put a little plus symbol there. I'm going to double click on that. And that's just going to copy the formula down here. Okay, then what I want to do is, okay, this question's asking for, what was that again? This question's asking for the pressure. So I'm going to have Excel calculate the pressure. this is the ideal gas pressure. You know, P is equal to nRT divided by V. Now, I could pick any volume I want, you know, and I can pick any amount. Usually, if I do this, they just want to see that it's becoming more ideal as we go to higher and higher temperatures. So you know what? I don't want to even look at the previous example. I want to pick something easy. So I'm going to pick an N of 1 mole and a volume of
1 liter.
1 liter. Let's do that. That's going to make my life a little easier, just for comparison. So the moles is 1. Okay, so I can do this. How many times am I going to need R? I might need R more than once. And so what I'm going to do is I'm going to write R down here maybe, as in case I need it for additional calculations. E206. Fix that. E206. I probably, if I had a better plan, I could organize it better. But, and so this is going to be liters atmosphere per mole Kelvin. All right, so I need nRT. So I'm just going to take R times T because N is 1, V is 1. So this is going to equal, okay, now I'm going to have R here. Okay, but this cell is what we call fixed cell. However, I'm going to copy this down. And so as I copy this down, what Excel is going to do is it's going to go B7, and the next one is going to go B8 and B9. I don't want 7 to change. If you don't want something to change, do you know how you do it in Excel? If you don't want something to change, you put a dollar symbol in front of it, like that. And so what's going to happen is this is going to keep the B7 all the way down. And that's what I want. However, I want the temperature to change. And so I'm going to just do times, and then I'm going to times it by this cell, B2, like that. Okay, now look what happens when I click on this, and then I copy it down. When I click on this and copy it down, you can see that B7, it's still B7. But it went from B2 to B3 now. Okay, when I look at the next cell, same thing. B7 stayed B7, but now it's B4, the temperature. All right, so these are the pressures in atmospheres. I'm just doing atmospheres because it doesn't really matter if I do atmospheres. How many sig figs am I allowed? I can adjust the number of sig figs here by clicking this little thing up here. So I'm only allowed 3 decimal places. I mean, no decimal places here. So I'm going to make this, I'm going to make it 3 sig figs. Well, I'll carry 1 extra. All right, now I'm going to calculate using the Van der Waals equation. So let's take a look at Van der Waals equation here. You have it memorized?
Almost.
Wow.
That one's a little bit longer.
Yeah. You don't have to memorize it. It'll be given. The calculations of the Van der Waals equation, it seems like algebra. And you would think algebra is not so difficult. But the calculation with Van der Waals, I don't know if anybody's gotten to that particular problem where you have to calculate the volume. Calculating the volume is not so easy. Can you see why?
Yeah, twice.
Yeah, calculating the volume, you think it's easy because it's just algebra, but it's not. the volume calculation can be horrendously difficult. And so pressure is easy. Calculating pressure using van der Waals is simple. And so this problem is not too bad. We can do that. But calculating the volume is much more complicated. And if the math gets too complicated, we have one fallback method. Do you know what that fallback method is? Like the method of last resort.
Brute force. It's my favorite.
There are different ways to brute force this. How do you brute force this for calculating B?
How do I do it?
Yeah, or what do you think?
So what I do is I will input a number
Mhm.
as close to the answer as I can find, and then I will just slowly increase the significant figures until I get the answer.
Oh, good.
That's how I normally do it.
Yeah, the brute force is a guess and check method. So we already know where the answer should be ballpark because we have the ideal. And so it should be somewhat close to the ideal. It shouldn't be crazy as far as deviating from ideal. It could, but at least we have a ballpark. And then we just keep guessing until it converges. And so, I wouldn't even bother changing this. If I'm looking for a volume, I'd use ideal gas law first, get a volume, target volume, and then either drop it or increase it. And then drop it or increase it and see what happens. I'd plug in NRT and see how quickly this converges onto NRT. So, this is going to be constant here. Fix that. All right, now we're doing chlorine. For chlorine, we have to look at what A and B are. A gives us an indication of how sticky they are, and B gives us an indication of how much volume they occupy. But do we have A and B for chlorine? No. I don't see it. So let me take a look at the example. So I have to go back to the example. Yeah.
Yeah, I can see it.
They did a volume of 2 liters. I did a volume of 1 liter. That's all right. They did 1 atmosphere or 1 mole. That's good. Okay, A is equal to 6.34 bar per liter squared. Bar liter squared per mole. And so let's go ahead and plug that in. 6.34. Bar liters squared moles to the minus 2.
Professor, can I ask a question about the units?
Yeah.
Why is it read as bars per liter squared?
Bars times liter squared.
Per mole squared minus 2. What does the mole minus squared 2 mean?
It depends on the square of how many molecules there are in a liter. The more molecules you have in the liter, the more the stickiness is going to play a factor. The further apart the molecules are, the less significant this is. The closer they are, the more significant it is. And these are electrical attractions. Electrical attractions tend to decay by what we call the square of the distance. The further apart they are, then it drops off dramatically. As you get closer and closer, the interactions grow. It's not linear. It's not a linear decrease. It's a squared or non-linear.
I'm just curious why they write it, where is it in a line like that? Because another way that it could be written is bars per liter squared over mole squared.
They do it. This is often done.
I don't. Simplicity.
It doesn't matter. This is often done this way, or the way you mentioned. I don't like to do this way, but sometimes it's helpful if you need to write everything on one line.
Yeah.
Yeah. Normally in a paper, you don't write a slash. You actually write a horizontal line, and then you bring the moles underneath. So this would require 2 lines of space. They don't like to draw draw like a forward or reverse flash or whatever. All right, B is 0.0542 liters per mole. I'll just do it the same. .0542. Yeah. All right, now I'm going to rearrange the van der Waals equation to solve it in Excel.
Do you have to convert that to the A value to atmospheres?
Yeah, we'll do that. We're going to have to convert this to atmospheres because my R is an atmosphere. So I'll do that up here. Or I could do it down here, either way. Usually I just plug everything into the equation and then convert it into the equation. So let's take a look at the van der Waals equation again, and then let's solve this for pressure.
They have it like equaling pressure.
Oh, do they already solve it for pressure? Okay, that's saves us.
Page 230, right under the table.
Okay, there it is. So I don't have to do much. I'm going to just plug this in here. So it takes some time to set it up, but maybe this saves us time. I don't know. This is going to save us time. So we have P is equal to nRT divided by V minus NV minus N squared A divided by B squared. This probably doesn't say, I mean, it's only 3 calculations. And so this may not save us much time, but we're doing Excel today, so let me talk about Excel. If we had 100 calculations, this would save us a lot of time. All right, so I'm going to just set up the equation equals. So now we need N. N is just 1. So, and then we need R. So I'm going to just click on this cell, but I don't want this cell to change. So I'm going to do the same thing. I'm going to go $7. Also, if I don't want B to change, I put a $sign in front of B as well. So
For vertical and horizontal.
yeah, exactly. All right, then I'm going to times it by the temperature. The temperature is equal to this cell, so I'm going to go times, and then this one I want to change, so this B2. Okay, this is going to be divided by V minus NV. So I'm going to put it in parentheses. V I had is 1 liter, so I'm just going to type in 1 minus NV. Okay, N is 1, right?
Yes, but we cancel out N too. Because both the N's are 1.
It doesn't cancel.
They don't?
No, they don't. It would cancel if it was N times V. Then I could factor out N out of this.
Okay.
But it can't cancel right now. So N is 1, and then I'm just going to multiply this by B, which is this cell. I mean, subtract it by this cell here. But again, I don't want the 7 to change, so I'm going to put a $sign in front of that. And so I picked 1s as easy numbers to save some. And I don't want this to subtract it in the denominator. So what I'm going to do is I'm going to put another set of parentheses here, just to make sure that it calculates everything in here and then subtracts it from this. So N is 1, so it's going to be 1 squared times A. So this is A. This is going to be divided by B squared. Well, B squared is 1 squared, which is 1. So I made the numbers easy, but if your numbers aren't easy, then you just plug it in.
Wait, so
Uh-huh.
your equation, you forgot to put the dollar sign in front of the 7 on D so that we don't change D.
Oh, okay.
And don't we have to convert it as well?
Oh, yeah, I forgot to convert it. All right, so I'm going to do the conversions here. And what I'm going to do is I'm going to convert R. And to convert R, which is B7, I'm just going to multiply this by 1.01325 bar per atmosphere. Okay, and then let's see what happens here. Is that right? So B7, 101,325. Just check it. So if I look at the formula bar, which is this here, let's check to see. So pressure is equal to nRT. N was 1, R B7 times T, which is B2. And then I converted the R to bar. So nRT, that's right, divided by V minus NB. Divided by V, which is 1, times N, which is 1B. This is F7, correct?
Yeah.
Minus N squared, 1 squared is 1. Divided by B squared, which is also 1, times A. You plugged in there. Okay. Uh-huh.
1 minus F7. Sorry, I'm trying to. So I can do the thing on my calculator.
Okay, 1 minus D7. Did I get that? Oh, F7.
Yeah, that's correct.
Is that correct? Yeah, D7. And then here, 1 minus F7, yeah. Okay, does that look correct? Yeah? All right, to make it a clearer comparison, we'll get it to the same number. I'm going to calculate the percent error. The percent error is going to be the experimental minus theoretical. Which one would be theoretical? Which one do you think would be experimental in this case?
Theoretical is the ideal. Or, right?
Well, now theoretical, we're going to use the real gas law because that should be more accurate. The one that's more accurate should be it. The experimental we'll just call the ideal. And so we'll just do, this is just going to be experimental minus theoretical divided by theoretical times 100%, or I can convert it to percent in that. But I'm going to put some parentheses here, so it doesn't. So that's a 15.7% error. So we can see the higher the temperature, the smaller the deviation. But how often do you work at 400 degrees Celsius?
Not very often.
Not very often. And so definitely the ideal gas law is working a lot better here. And this tells us what? This tells us there are two things that are making chlorine behave less than ideal. One is that the chlorine molecules themselves are a little bit sticky. And the lower the temperature, the stickier, right? And then two, what? to the volume. But the situation with the volume is this. This is the pressure in what units? Yeah, this is the pressure in atmospheres. This is the pressure in what? Bar. So it's not a fair comparison, right? And so I need to do one thing here. Either I need to convert the atmospheres to bar, which I'll do, or the bar to atmosphere. I'm going to convert the atmospheres into bar. So this is in atmospheres. And then I'm going to calculate the pressure ideal in bar. The reason I'm going to do this is because it's an easy conversion. So we're going to take this times 1.01325 bar per atmosphere. And that's going to give it to us here. Is that right? Okay, now did that correct my equation? If you look at this, do you see that when I inserted the cell D here, it's still taking cell C. You see that? Yeah. For my percent error. So what I'm going to do is I'm just going to change it. I don't want it to do this. I want a bar-to-bar comparison. So I'm going to change this to D here. D for D. And then do that here. So now this is a fair comparison. This is the ideal gas law pressure in bar. This is the van der Waals pressure in bar. Now, is the van der Waals equation perfect? No, it's not perfect. These are empirical correlation factors. You know, they try to get an equation that more accurately describes the behavior of a gas, and this is one of them. But this one also deviates, like the ideal gas law deviates, you know, from the actual observed pressures and the actual observed volumes. And so they have another equation. They have an equation called the Virial equation. In the Virial equation, do you know how many terms there are?
More than 5.
Like an infinite number. Depends on how many corrections you want to add to it. So obviously, if you have an infinite number of adjustable parameters, then you can fit anything. But it becomes less and less meaningful. And so this is still not perfect, but it's better. Especially so if you're using chlorine, which is a little bit sticky, then you got to worry. At low temperatures, stickiness becomes a factor. And the volume is also a little bit bigger. Let's take a look at the A and the B here. What was it? 6.34. 6.34. And so chlorine's about as sticky as what?
C2H6.
C2H6.
That would be the closest one.
Yeah, all right. Yeah. So it's about as sticky as ethane. It's actually a little bit more stickier than ethane, but not as sticky as propane or sulfur dioxide. You know, propane's a lot more stickier. Propane's a lot easier to liquefy than ethane. You know, you can get liquid propane in a propane tank. Now the volume is 0.0532, I think it was. And so as far as volume of the molecules themselves, it's 0.053. In other words, it takes about 53 milliliters of volume per mole. So yeah, it's around here. Nitrogen trifluoride, about the same volume as that. What's the biggest one?
Propane.
Yeah, propane takes up a lot of space. And so if you had a mole, 20, what is this? Under what conditions of this? Well, standard temperature and pressure for gases is what?
25 degrees Celsius at 1 bar. But this is at 10 bar, 300 degrees Kelvin.
Yeah, this is whatever conditions they had. 10 bar, 300 Kelvin. All right.
That's about 27 degrees Celsius, give or take.
Yeah, close to room temperature. 2 of them more. But anyway, we got to look at the temperatures and the pressures. So we see some deviations here. So ideal gas law deviates, for real gases. Yeah.
It's a little under 10 atmospheres in there.
It's still a 6% error, right? 400 degrees Celsius. But it will get smaller as we keep increasing temperature because, the faster the molecules are moving, the less they can interact with one another. All right, other questions? Were there any other questions? No? Oh, what did you guys get for the temperature? When you mix the hot water with the cold water? 50 degrees. Is that the right number of sig figs? 50.0 degrees Celsius. How did you predict that? How did you predict the temperature?
I have the theorem. Find my work.
Just took the average.
Yeah, to take the average. Yeah, I mean, we started at what, 20?
Here it is. Yes, 20 degrees Celsius.
And then we went up to 80.
Yes.
And that was, we mixed them together, right?
Yes.
And so half of it came from 20, the other half came from 80, and what's right in the middle? 50. So it came out to 50 degrees C. So you'd expect the cold water to warm up by 30 and the hot water to cool down by 30, right? And what was their theorem that you used?
M1 times delta T1 times C1 are constant, which is the
Okay.
it was 4.184 for water. That was my constant. Is equal to M2 times delta T2 times C2. I used the 4.184
Okay.
per mole Kelvin.
Okay, so you did it by calculation. But that calculation has an equation. That equation is based on the first law of thermodynamics. And so everybody has an intuitive sense of the first law of thermodynamics. The first law of thermodynamics states what? There are different ways you can say that. One way is energy is conserved. Another way you could say that is energy is neither created nor destroyed. And so this is how we can kind of figure it out based on this. So if one body cools down, the other body's got to warm up, in this particular equation. And so when we're thinking about energy, oftentimes we'll think in terms of heat. Do you know what the symbol for heat is? Or do we just call it Q? That's heat. This is like kinetic energy, right? Heat. And normally when we think about transfer of kinetic energy, we think of warming and cooling. Heat transfer. This is the transfer of kinetic energy. This is why like a vacuum thermos doesn't work at transporting heat. Because you could have a hot surface over here and a cold surface over here. And the hot surface has lots of kinetic energy. But if we have a perfect vacuum here, then this is going to stay hot forever because there's nothing to transfer the heat over. And so this is the concept. But the problem is can you get a perfect vacuum? No. And so if there's a little bit of gas in here, that little bit of gas will pick up some kinetic energy from collisions with the hot surface and transport it over to the cold surface and warm the cold surface up a bit. And so heat transfer is just the transfer of kinetic energy. From hot to cold. So when we're looking at heat transfer, what we do is we define two things. So we have something called the system and the surroundings. The system is the object or the reaction. Object, because object or reaction. We like to keep things simple. We don't like to change too many variables. So when we're thinking about an object, we think about the kinetic energy of the object. Is it hot water or cold water? However, when we think of a chemical reaction, we think in terms of potential energy. You know, is it explosive, potentially, or is it stable? And so what we're doing here is we're just looking at the kinetic energy transfer, that is heat transfer. We aren't looking at any potential energy transfer because, you know, the mixture here is water. So we start off with water, and we end up with water and water. And so it's just water. And that's objects here. Versus a chemical reaction. In a chemical reaction, we do it a little differently. So first I'm going to just talk about objects here and transferring heat in an object. And so what we want to do is, you know, the surroundings, this is the object of the reaction. The surroundings is what we call the rest of the universe. So what I'm going to do here is I'm going to call, let's call the system in this case, it doesn't matter, I could call the system the hot water or the system the cold water. And so in this case, I'm going to call the system is going to be the hot water. And the surroundings I'm going to call the cold water. How we define the systems and surroundings is up to you. You know, however you want to define it's fine. And so this is another way of writing the first law of thermodynamics. The first law of thermodynamics is this. Q of the system is equal to minus Q of the surrounding. And then we have a sign convention here. If Q is less than 0, heat is lost. And we call it exothermic. If Q is greater than 0, then heat is gained. And we call it endothermic. I want to change this pen. This just means it's the opposite sign. this does not mean it's exothermic. It just means it's the opposite sign. So if the system's exothermic, which would be negative, then the surroundings must be endothermic. Negative times a negative gives us positive, and so that would be endothermic. If the system's endothermic, then the surroundings must be exothermic. And so the negative is just to change the sign, because we can't have both the same sign. That is, we can't have the system endothermic and the surroundings endothermic, because that would be a violation of the first law of thermodynamics. The first law of thermodynamics says energy is neither created nor destroyed. And so if the system loses energy, the surroundings must gain it, or if the system gains energy, the surroundings must have lost it. Now, when we look at objects, the amount of heat is going to depend on what? And so this is just for objects. Here. The amount of heat is going to depend on the temperature of the object, and the amount of the object. And so the amount of heat that's gained or lost in this is going to equal the amount times C times delta T, where C is going to be the specific heat. The specific heat is going to relate, or going to be a conversion factor between temperature and calories or joules. So for example, water has a C of 4.18. Do we want to go 4 sig figs? We'll go 4.184 joules per gram degrees C. Yeah, a little bit different. This is for water, which is fairly high. It takes a lot of heat to heat up water. Versus if you had copper, copper is much less than 1. It's like point something. It's pretty small. It doesn't take much heat. So, in this case, so we have the system. Q is the hot water. And this has got to equal minus Q of the cold water. And so any heat lost by the hot water has to go into the cold water. And so, like Alex was doing the calculation, we could figure it out. It's going to be the amount times C times delta T of the hot water. This is going to equal the amount times C times delta T of the cold water. Now, the amount, how many grams did we have, or milliliters? We had 50.0 milliliters, and then the first thing we have to do is we have to convert it to grams, because C is in grams. And we're just going to use 1.00 grams per milliliter. And then we're going to use C, which is 4.18 joules per gram degrees C. And then we're going to use delta T hot. Delta T hot is T final minus T initial. So I don't know what the final temperature is, but the initial temperature of the hot water was 80. Was it 80.0 or just 80? 80.0 degrees C. This is going to equal the amount of cold water, which is 50.0 milliliters. We're going to convert it into grams, 1.00 grams per milliliter. And then we're going to use the specific heat, 4.18 joules per gram degrees C. And then we'll multiply it by delta T. Delta T will be T final. T final, they should come to the same temperature. So T final for the hot water is the same as T final for the cold water, because eventually they'll mix. But T initial is different, 20.0 degrees C. Yeah. I could have canceled it out up here, but I didn't. And so we'll just cancel this out. Is that what you did, Alex?
Yes. Just, yeah, cancel that.
And then solve for T final. You solve for T final. T final is 50.0 degrees C. So this is an application of the first law of thermodynamics to objects. And so what we're doing here, in the lab is a little bit different. And so what was this first part called in the lab, hot and cold water?
Yes.
We're going to define their system the same. Q of the system is going to equal the hot water. And we have how many milliliters? 50.0 milliliters of hot water. But the surroundings is going to be a little bit different. This is going to equal minus Q of the surroundings. And the surroundings is going to be, okay, this is going to be minus Q of the cold water. The problem is some heat was lost, not just to the cold water. So the hot water lost heat to the cold water, but also some heat leaked out of the styrofoam cup. The styrofoam cup also absorbs some heat. And so what we can say is we'll have the cup, and then, the probe, and then, there's a little bit of air above there, plus the air, plus the lid, the plastic lid. And then maybe a little bit went onto the counter or the tray, and the air outside, maybe the walls. Maybe some heat hit you, warmed you up a little bit too. Maybe, did you feel any heat? So the problem is that's a lot. Do you have the specific heats for all these? No. Do you know? No. And so what we're going to do is we don't know what all that is. So what we're going to do is we're going to call this. This is going to equal, we say, minus Q of the cold water, which we can calculate that easily. And then everything else. And so everything else in this case we're going to call the calorimeter. Here. And so all this stuff is the calorimeter. Calorimeter is just some insulated container. If it were perfectly insulated, this container, then the Q of the calorimeter, the heat absorbed by the calorimeter would be 0. If it were perfectly insulated, but it's not. And so we have to find out how leaky our calorimeter is. And so we're going to do this. So if we did this, let's say we mix hot water at 80 and cold water at 20, and it was 50 and 50. What's the final temperature going to be? Do you know what the final temperature is not going to be 50? Do you know what the final temperature is going to be? It will be a little colder or hotter? It'll be a little bit colder than 50. The reason it's going to be a little bit colder than 50 is because we're going to lose some heat to the calorimeter. And what we're going to do is we're going to find out how much heat we lose to the calorimeter. And so this is how we do it. I know the equation for the hot water. The hot water is equal to the amount times C of water times delta T of the hot water. Okay, then delta T of the hot water is just equal to T final minus T initial. This is going to equal minus the Q of the cold water. The cold water is the amount times C times delta T. Okay, this is T final. T initial, it will be T hot. Okay, over here, the delta T is T final minus T initial, but T initial is T cold. The two T finals should be the same. That is, the T final of the hot water should be equal to the T final of the cold water. If they aren't, then heat's still being transferred. And if heat's still being transferred, then the temperature should be changing. Yeah. Okay, but what about the calorimeter? So this is going to be equal to the amount times C of the calorimeter times delta T. Do you know how many grams of calorimeter we have? And do you know how many grams of, well, we can measure how many grams of cup. And then, do you know how many grams of probe we have? Air? All the, no. You know what we say is the amount of calorimeter is only one. Did anybody use more than one calorimeter? There's only one calorimeter. And so this is always one. And so this is our unknown here. Our unknown is going to be how many joules of heat are lost per delta T for a given temperature change. And so this is what we're going to solve for. What's the delta T of the calorimeter, though? The delta T of the calorimeter is going to be T final minus T initial. Now, T initial is going to be the same temperature as the cold because the cold water was in contact with the calorimeter. T final will be the same for all of these. They'll reach the same final temperature. So we only need 3 temperatures in order to do the calculation here. And the 3 temperatures are the temperature of the hot water. What was the temperature of the hot water?
90 degrees C.
90 degrees C.
Yes, close to boiling point.
Close to boiling.
Right? Because we're supposed to use hot water.
You're supposed to use hot water. When did you mix the hot water with the cold water? The problem is it might start out in 90 degrees C, but what happens as it sits? It cools down. And so at the time of mixing, what was the temperature? Was it 90 degrees C right at the time you mixed it? In fact, do you even have the temperature at 6 minutes recorded? You have it recorded, but is it accurate? No, it's not accurate because the probe was probably not even in there. Or maybe the probe was in there, but it's not an accurate temperature. And so we have 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. But 6 minutes, we don't use that number. 6 minutes, it could be anywhere over the place here. And so it might have started at 90, but what's going to happen with time? It's not a perfect insulator. So with time, it's going to cool down. So this is called a cooling curve. And what we're going to do is, we don't know what the accurate temperature at 6 minutes is, but we're going to extrapolate it based on the cooling curve. So based on the cooling curve, 6 minutes should have been here. So this should have been the time, the temperature at the time of mixing. Here. So this is going to be T hot. T hot is extrapolated. The actual data point may be here or up here, somewhere. So we're going to extrapolate that out. So does somebody have their data? Let's go ahead. And what we're going to do is we're going to use Excel to do this, to make our lives a bit easier.
Well, I've heard so far it sells at it.
All right, go ahead and give me the temperatures for the hot.
Of course. At 1 minute, I had 71.7 degrees C for hot and 20.5 degrees C cold.
All right,
You want me
well,
to
just give me the hot.
Okay.
Okay, one thing is, how many minutes of data did we collect?
I collected 15.
15 minutes of data. Another nice thing about Excel is Excel can recognize a trend. Do you see the trend here?
Yes.
1 to 2. What I do is I just grab the bottom corner of the box and then just scroll down until it hits 15. There. And so it'll fill it in for me.
Okay.
So I don't have to type it. Okay, so you have 71.7 and then what?
70.5.
70, see, you told me 90.
69.3.
69.3,
Yes. 68.1.
68.1,
67.1.
67.1.
And then at 6 minutes, I had 47.4 after mixing.
Okay, 47.4 after mixing, but that's not the temperature of the hot, that's the temperature of the mixture.
Yeah.
So we cannot use that.
I'm not going to use this data point here, so I'll mark that in red. Instead, what I'm going to do is I'm going to see what the cooling trend was. So if I want to see what the cooling trend is, I just highlight the data here like this. And then probably the easiest is to insert. We're going to insert a scatter plot, which is this one here. That. So this is my cooling plot here. And then what we're going to do is we're going to just extrapolate this out to 6. So how can I extrapolate this out to 6? Well, what I'm going to do is I'm going to do this. I'm going to right-click on a piece of data here. And then what we're going to do is we're going to add a trend line to see what the trend looks like.
Oh, I did. I did.
Okay, I'm going to format this. I have a linear trend line here, and there are two boxes on the bottom, display equation and display R squared value. I want to click these two boxes on the bottom of this, and then C. And then maybe I'm going to change the line to make it a little bit more visible. I'm going to go with a solid line, and then I'm not going to make it blue. I'll make it orange.
Blue is one of my favorite colors.
I just did the border. I didn't want to do the border. Okay. Well, anyway, you can change it yourself if you like. Yeah, that's all right. Take a look at the R squared value. This is what we really want to do.
If I had an R squared of 1, then that means it's perfectly linear. But you can see I'm deviating a little bit from linear behavior. The more 9s, the better. I have 2 9s and an 8.
So what I'm going to do is I'm going to change this. Yeah, it's not a huge deviation. But I'm going to change this to exponential. When I change it to exponential, what happened?
R squared got more times?
Yeah, 3 nines. 3 nines is better than
2 nines.
2 nines. Let's go to logarithmic.
Oh,
Is that better?
No, that went far down.
No, this is even worse. 1 9 on this fit. And look at the fit doesn't even hit the data. Doesn't look very good. Let's try polynomial.
Okay.
Polynomial looks
Pretty accurate, yeah.
pretty good. 3 nines and a 7. Let's compare that with exponential.
Exponential.
3 nines and a 3. So far, which one's the best fit? Polynomial is the best fit. Let's try power. Moving average? No, moving average is something totally different. Now, I have polynomial with second order. Okay, what I'm going to do is I'm going to go to third order.
No, it's just,
What happened there?
it's just a straight line.
Third order polynomial is a perfect fit. Do you see that? What if I go to fourth order? This goes up to sixth order.
It's still one.
But you know what? I don't have enough sig figs. Maybe it's rounding. So what I want to do is I'm going to format the data series here. I'm going to format the data series and I'm going to put in some more sig figs.
The amount of sig figs is exponential.
That's weird. All right, format trend line label. I'm going to go to number here, and then I'm going to increase the number of decimal places to, let's go with 5 decimal places here. Because that 1 could have just been rounded, right, the 1. And so to prevent rounding error, I'm going to go 5 decimal places out, and then I'm going to go back and look at the 1s. So go to format trend line. So this is fourth order. How about third order? Remember third order said 1, but it's not 1. And what was second order?
3 9.
That was because of rounding error. Second order was 3 nines and a 6. We were thinking it was perfect. Then we go to third order, fourth order. Let me see if I can get it. This is third order. 4 nines, good. Fourth order. But it could be rounding still. So let's take it out to fifth order. Actually, maybe it is still rounding. You know what I'm going to do? I'm going to format trend line label, and I'm going to go to, let's go to 10 decimal places.
10 decimal. That's a lot, huh?
That's a lot of decimal places. But with 10 decimal places,
Like how big
this is, what order is that? Fifth order? Let's try sixth order.
Yeah, that's just a lot.
Well, this is pretty good because how many nines do we have? 1, 2, 3, 4, 5, 6, 7, 8 nines. 8 nines is a great fit, right? But people hate doing this because number one, the more orders you add on here, what's going to happen? Yeah, you're going to get eventually you're going to get a perfect fit. If you had an infinite number of orders, like the Virial equation, you're going to get a perfect fit. It's going to look like this, you know, and then one up here will grab it. But, and so in terms of physics, this is meaningless. And so what we do is we look, you know, we need to have some kind of, you know, we could fit it to any mathematical equation. You know, it could be really bizarre mathematical equation. What we have to do is we have to figure out how does that apply to kinetic molecular theory. You know, because these equations, this is called an empirical equation, but eventually we want to be able to derive an empirical equation from theory, right? And so if we want to try to derive it from theory, then we need to know. And so Newton, let's look at Newton's law.
I didn't know Newton had a law of cooling.
Yeah, Newton's law of cooling.
H times A T minus T divided.
And so we want to have this kind of related to actual theory. And what does it look like? It looks like Newton's law of cooling is exponential with an extra factor, with a constant. And so what we're going to do is we'll just do an exponential. They'll be as close. It's a little bit more complicated than that, but we're going to fit this with exponential here. The exponential is going to give us 3 nines here. Now what we want to do is we want to go out to 6. And so what we can do is we extrapolate the line out to 6.
I'm still going to say 66.
And the way we can do that is we can go to format axis. Or actually, do I need to do this? No. Let me do this way. I'm going to format the trend line here. But do you see this format here? It says forward, backwards. So forward allows us to forward extrapolate the line. Backwards allows us to back extrapolate. So we're going to forecast it forward by 1 period.
Why not 2 periods, sir, so that we can get more accurate?
Because we only need to go to 6. So this is what Excel predicts the temperature to be at 6 minutes. And so what is that number there?
Looks like exactly 60 seconds.
Well, if I hover over these dots, I might be able to see the number. I don't see the number there.
Oh, it's series 1 trend line.
Yeah. And so, this is what we're going to do. We're going to use this here based on this equation. So this equation just tells us the temperature is equal to this times E raised to this power times X. And so we just put in X. X is going to be 6 minutes here. And then we can calculate the temperature at 6. So we're going to use this to calculate the temperature at 6. Does that make sense?
Yeah.
All right. Now, the cold water, the temperature doesn't change. So the cold water, it really doesn't change much. And so you could probably use linear for the cold water. But the problem is when we mix this, what we have is it's like mixing hot and cold water in a bathtub. It doesn't mix instantly. And so it takes time to mix. So after you mix it, the temperature might fluctuate a little bit depending on how well mixed it is, but eventually it's going to settle down. Once everything is properly mixed, then we'll see Newton's law of cooling happen out here. So what we're going to do is we're going to ignore 7, we might ignore 8, and then we'll just go from 9 to 15. From 9 to 15, what we want to do is we want to see the trend line for the cooling, and then back extrapolate this to 6 minutes. This would have been the temperature if you could have mixed it in 1 millisecond, or 1 microsecond, or 1 nanosecond. If you could have mixed it in 1 nanosecond, then it would have been here, and then it would have cooled down with this trend that goes out to 15. Does that make sense? And so we're going to back forecast this and then show that. In fact, we're going to put all 3 graphs on one plot. And we'll put all 3 graphs, and we're just going to graph everything and then just shorten. So we're going to go to the computer lab, and then we'll make a fancier plot for this in the computer lab. Are there any questions for this? No? All right, so let's head over there.